All right, first up, we have Mark Willarth with H&P. He's going to talk about non-orthogonalities.
Hey, everybody, and thanks for returning after lunch. Hopefully you all had a good meal. So I think I know many of you here, but I'm Mark with H&P. I've been doing survey corrections and various forms of downhole tools and things for over 15 years. Was with Magvar, we got bought by H&P. And today we're going to be talking about a often overlooked aspect of survey sensor errors, which is alignment issues and non-orthogonalities. So alignment errors tend to cause a lot of confusion broadly in the domain of people using surveys because there are operators who aren't sure exactly how to qualify if their wellbore's been accurately placed. You might have tool vendors who have no idea what specification they're supposed to build their tool to necessarily. Or sometimes you're just having a conversation with an MWD company who you're trying to correct their surveys and you tell them you can't because of some error they have not been thinking about. And a big reason why people don't think about it, a major source for some of these problems is that years ago and change, when Ezra was out on the rig floor with his single shots, there was a decision made to not include alignment errors, MWD sensor alignment errors in the error model. And so this is a paragraph some of you may have read in 67616 that says they're going to be omitted. There's too many different random alignments, and it would be a lot of work. To add to the confusion, though, if you don't read Williamson's paper and instead you actually look at the error model itself, you might see several lines that do refer to misalignments. And so one thing I would like to clarify, just in case there's confusion, because there is often confusion, is that this is not talking about sensor misalignments. This is talking about misalignments between your drilling tubular and the borehole. So anything around how your sensors are actually placed is not included for that. Because there's that gap, though, I thought it'd be good to at least put some of this on the record. You know, we have that one note. I've never met anyone who actually is a copy of Andy Brooks' analysis. And so I do trust Andy's work in general, and I've looked at this problem myself, but I figured I would introduce this today so it's there. We can have a discussion about it. And we'll talk a little bit about how non-orthogonalities impact surveys, why they're not in the error model, and why I would still advocate them not being in the error model. But then also how this adds complexity to a lot of surveying workflows, and what conversations you need to have to smooth some of those complications. One phrase that I will be using a lot in this presentation, again, I've not replicated Andy's analysis. There are a lot of ways to do this. I would like to present a way. I'm not saying it's the best way. I'm not saying other ways that might be a little different or wrong, but this is a way to consider it, and it is a way to talk about it. In particular, the way I will talk about it, if I say non-orthogonality, I'm referring to a sensor triad not being mutually orthogonal. If I say misalignment, I'm going to try to hold myself to this. If I say misalignment, that means the triads are orthogonal, but they are not in line with each other. So a non-orthogonality is one sensor moving, and then a misalignment would be a bend or a twist in the tool. So with that, let's look at what actually happens with a non-orthogonality on a survey station. So if we imagine having, to simplify a lot of this, we're going to look at two axes of a sensor. So an ideal sensor, you have, let's say, an X and Y. They start mutually orthogonal, and you are trying to measure some cross vector, and they each get a component. So you have an X component that is being read, a Y component that's being read. You produce your cross axis vector. Great. This is what we assume happens in an MWD tool. If we move one of those sensors, if we create a non-orthogonality, we're going to say the X in this case, for reasons I'll talk about later, it is now not going to read precisely what it was supposed to. The X-axis is not going to have the theoretical value we would hope for. Again, for the sake of going through this pretty quickly, for the sake of just getting the topic out there, if we think about some hand-wavy trigonometry, what actually happens is the sensor that has shifted will read a little bit less of the component it was supposed to, and it will read a little bit of the component it was not supposed to. And so your sensor reading you have is going to be the theoretical sensor reading. Woo. Your theoretical sensor reading times the cosine of some angle, and then what your perpendicular vector was supposed to be times the sine of some angle. And this is the nature of the simplification that is alluded to in the error model. And so this is kind of where it all starts. Again, I do oversimplify and rush through some things just to keep this on track for time. This could be a very long presentation. We do long trainings on it. This does generalize to an arbitrary number of non-orthogonalities. This does generalize to other things. And also, if you want to keep your life simple, any misalignment, the idea of the triads not being with each other, can be generated through multiple non-orthogonalities being added on top of each other. And so this is sort of what happens to a survey sensor measurement when we have a non-orthogonality. If we get to what happens in the error model, again, what I assume some amount of what Andy did is on this vein. If you look at an individual survey measurement where you have an individual sensor reading, you can take that cosine of your non-orthogonality angle and lump it in with a scale factor that would have been applied to your survey. This cross component, again, for the purposes of a single survey measurement, this, your perpendicular component multiplied by your non-orthogonality, is just some fixed thing that's being added. For an individual survey measurement, there is, for any non-orthogonality, an equivalent scale factor and bias you could apply to get the same sensor output. And so you can ignore, for the purposes of a weighting function, an isolated non-orthogonality. This also helps us get to one of the big questions that comes up in terms of, at what point do you fail a tool because of alignment? At what point do you have to send a tool back to get recalibrated? At what point do you say it's too much? You can actually calculate equivalent scale factors and biases for levels of alignment error. It turns out the scale factor side of this is more or less insignificant. To actually get a meaningful scale factor error out of a non-orthogonality, you would have to have several degrees of alignment error. And if your tool is in that rough of shape, you're probably sending it back anyway for other reasons. The bias component, however, is actually meaningful. So you do have, at some relatively small angular errors, meaningful biases. And this is where it's important to have a holistic process as a service provider or a vendor, because depending on how you're going to use the tool, the combination residual bias and the combination of potential error from an alignment, it can quickly add up. In this case, though, the environment is important because the size of this, you can think of it as a variable equivalent bias as you move the tool through different orientations, but it is going to depend on what that other axis is. So when we moved the X sensor into Y, the magnitude of the Y vector impacts the magnitude of this bias. A worst case scenario, though, would be your total field. You're drilling perpendicular to your total field for that sensor. And so you have this sort of maximum, influence. It gets a little trickier from an error model perspective when you have to think about the propagation mode, because again, this bias component of your non-orthogonality is not going to be constant survey to survey as you change your tool and as that cross-axis vector changes, but it will be bounded. As many of you know, I like to heavily advocate for the error model being an error model and not being a solution to all of our industry's problems. And so if your goal is to describe the positional uncertainty that is caused by an issue with the instrument, the error cone created by a big enough bias will encompass the positional errors that would be created by a non-orthogonality, because the amount of error that will be introduced is bounded by that cross-axis vector. If you are describing positional uncertainty for an operation, I'm a firm believer this is sufficient. If you are calibrating tools, if you are designing survey corrections, if you are doing all sorts of other things that we like to start with at the error model, it might not be sufficient. But again, the error model is for positional uncertainty. It can be used as a reference for some other processes, but it is not the end-all be-all for those other things. The practical implication here, if you are a service provider, if you are a tool vendor, is that when you are trying to do your error budget and when you are trying to design your QC processes, you need to think about the interplay of your survey QC, your alignment error you're going to expect, and the residual biases that are acceptable on your instrument. This can lead to some counterintuitive situations where if you have, for instance, a roll check procedure that has QC criteria bounded based off of a bias limit, you might not trigger that bias limit from a non-orthogonality. So there needs to be a little bit deeper analysis there to make sure you're actually covering this error in depth. It might mean that an instrument is accurate for certain orientations and is sufficient for, for instance, drilling vertically and not accurate for drilling horizontally, because the orientation dependence of some of these errors and the magnitude being variable can mean different things for different operating states. The other thing that is actually a bigger point to discuss, which is why I'm dedicating a whole section to it, is when you start doing survey corrections, these implications get even trickier. So how do survey corrections play into all of this? It's been mentioned a couple times already today. The multi-station tool code that most folks use has an implied 50% reduction of your sensor biases and scale factors for your magnetometers. If we are lumping alignment errors into this term, that technically puts a burden on the survey correction provider to either also reduce alignment error by 50% when they do their corrections, or reduce the residual biases to a low enough level that this is just your alignment error budget. In practice, what this can mean is that because you're often putting a new spec on the tool, there might be instruments that will pass a standard MWD QC and pass the standard spec, but will not be able to pass a corrected spec because of this implied better alignment. So this is the case where you might have, in particular in the US, where you have the tool provider, the service provider, they might be all very different groups. You might have someone who's surprised to find out their instrument is not suitable to be corrected, even though they're following your operational procedures for doing a survey correction. But it is possible to do, again, that you could also have your corrections provider do alignment corrections to an extent. It gets a little tricky because while those 20 some odd error sources are not in the error model, your correction algorithm could be given 20 some odd degrees of freedom if you want to. But once you do that, you get the ability to do anything. Once you start moving sensor alignments, you could just change the orientation of the wellbore if you want. And so that's where, again, I will present one way, not saying it's the only way, not saying it's what everyone will do, but one approach to handling this, to take the 20 degrees of freedom and make it manageable, to make your process something reasonable, is to make some assumptions as a corrections provider. So what we advocate for at H&P, because we will, from a correction standpoint, we will never handle the physical tool. So we cannot tell you if the axial accelerometer is aligned with the chassis. So for us, the axial accelerometer will define the chassis. We just do that by standard. So we will never apply an alignment correction to the axial accelerometer. This is also politically convenient for us because inclination corrections usually raise hairs, and if you start changing the accelerometer, you're arbitrarily changing inclination. A second convenience for us is we assume the y accelerometer defines the tool face. And so at that point, making those assumptions, you can actually dramatically reduce the space of your corrections. And in many cases, this is enough to get a lot of alignment corrections reasonably close. Again, these assumptions are safe to make because if it's wrong, if the axial accelerometer is not truly aligned with the instrument, you create an offset center, which is that misalignment that actually is in the tool code, and it's generally limited and randomized. If the y accelerometer, again, is no longer the right spot in the chassis, all you do is create a tool face offset, which does not impact position. It only impacts steering. So this is fine. And again, of those 20 degrees of freedom in practice, most end up being okay. Again, misalignments for bends are generally pretty easy to resolve and correct for. It turns out that non-orthogonalities in the axial direction tend to have low impact because we like to drill in straight lines. And so if the Z sensor is not seeing a large amount of change across an interval, a non-orthogonality towards Z mathematically becomes a bias and can be removed. The one that is really though the getcha though is the X and Y non-orthogonality, the cross-axis sensors. And so that's why I started my example with the BX and BY, because this gets you to a really interesting situation where non-orthogonality is easy to detect, but a unique solution is very difficult to confirm and have high confidence in. There's a presentation this morning about the challenges and uncertainty, and when you have the degenerate solutions, this is your fundamental degenerate solution. So identifying that the sensors are non-orthogonal is straightforward. You will get this double sine wave pattern on a roll test. This is very easy to identify. It's fairly easy to quantify the size of the non-orthogonality. But when you go to solve and correct for it, it is very difficult to be confident in a unique solution, because if you pick the wrong sensor, again, if your X sensor has moved and you restore a correction to the Y sensor, or vice versa, if you get it wrong, you've created a twist. And I'm sure many tool manufacturers will tell you that twists are one of the most bugaboo, annoying things to deal with. If you're drilling straight north, they tend to just be an azimuth offset, so it's completely unobservable. If you're drilling east-west, they create a dip offset. And so that produces a lot of challenges in a confident correction. I will say, again, with a very big US bias, some of our customers have figured out a way to just make life really easy for their survey corrections provider. We have one company who did not get to make it here, I believe, this stint, but has been active in ISCWSA in the past. We're in Colorado. They drill from vertical to horizontal east, flip 180 degrees, drill horizontal west, and they do it in one bit run. If we could just convince them to drill back up to surface, we would recalibrate the tool downhole. This is an amazing scenario if you get it. And this breaks all of the collinearities, and this avoids all the degenerate solutions. It's amazing. But if you're not doing that, you have this problem of, is it a reference offset? Is it a dip offset? Is it drill string interference? Is it a twist? And this is an unresolvable problem downhole. And it's also a really awkward conversation, because when you go to the customer, you know the survey is wrong. You have high confidence in how much it will move, because you can imagine the two solutions for resolving the non-orthogonality, but you don't know which one it is. So what do you do? Ideally, you could have good processes. Again, pre-run checks can do this. I know some areas they like to do east-west roll tests prior to picking up a tool. Sometimes that bound, the uncertainty is within an acceptable margin for a driller if you quantify how much it will change. But in other cases, you just need to trip and test the tool. Like if it is that important, if you are going to drill really far, you just need to go do that. So where does this leave us? Again, very, very selfishly as your error model chair, the big takeaway I want the group to know is that alignment errors are not in the error model, and we don't need to put them there. Also very selfishly as a correction provider, they are something you need to worry about in your corrections, and they are a conversation you need to have. So non-orthogonalities, from positional uncertainty perspective, are adequately modeled. They do exist. Hopefully hand-wavy trigonometry was enough to convince you we don't need to split out 20 more error terms. But that doesn't mean everyone else is off the hook. Tool providers need to worry about this, correction providers need to worry about this, and operators need to worry about this for their operational practices beyond just positional uncertainty. Hopefully this has been helpful and instructive. I think I've got some time for questions.
The presentation. On the first part of the presentation, you got the bias saying that the contribution depends on the orientation of the orthogonal axis. But the normal bias shift would be independent, right? You get the same shift. So you will look like a random contribution, and it doesn't affect the final position of the well is not altered by this random. You have enough change.
It depends, and so this is the other reason why the XY is really gets you, is that again, this is a subset of a much longer presentation where we talk through it, and I sometimes refer to non-orthogonalities as equivalent to a variable bias. It's a bias that is a function of your orientation. If you are so the places where it really matters for your EOU and for your positional uncertainty, again, technically, if you have a non-orthogonality towards the axial component of your tool and you're drilling in a straight line, then it becomes a bias, and it contributes the exact same way as a bias. The other impact you will have is for your XY non-orthogonality, it is like a twist. Not completely like a twist, but it's like it can create some variability. So it's a random magnitude, but it's not always a random sign. So there are times where it aggregates in one direction over the other, depending on. So tool face, yeah, it will depend on your orientations. I would say what we're doing now, which I still think is a reasonable, correct way to go, is to treat it as a bounding cone. Exactly how much you want to balance your bias contribution versus your alignment contribution in your sensor spec and things is open to debate, because it's a little conservative to assume it's a little conservative to assume a worst case, wherever that was. Here, it's a little conservative to assume a worst case of, oh, I'm going to be truly perpendicular to my vector. Yeah, that's probably conservative, but in some cases, it could be adding up. Yeah, it's not quite a fully random component, is what I would say. Just like a twist is not random in many cases.
For the multiple magnetometer assembly. So it's just additional comments on one. It's like you have actual alignment. Maybe like if you rotate it, normally rotating axis around the ideal axis. So normally we see some sinusoidal error.
Yes.
From the actual measurement. Normally if you average out or multiple measurement, it's going to be like randomly. So it's quite less. But yeah, I agree with you that please error.
And for an axial misalignment, it will randomize. And again, I would say from the perspective of someone who does not touch the physical tool, an axial misalignment is essentially equivalent to a center offset on the tool. Like you wouldn't know if is the issue that the sensor is not aligned with your chassis, or is the issue that the tubular your chassis is in is not aligned in the bore hole. You would not be able to distinguish unless you physically get to hold the thing. And so that one I would say actually could be considered this effect that is captured in the error model.
Another comment, I think it was like MCC mentioned about either the PT or the detail. Yeah, you can identify.
Here.
And a wrong slide back. No. I think you show the PT, yeah, something like this. For example, mismatch of the scale factor between the two axes may also cause a double sine wave.
So that's sorry. It's a nuance that's on the slide, but I didn't mention is that this is not only a double sine wave, it's also double signed in that it creates a positive and a negative deviation from your reference field. So a scale factor will create a positive or a negative deviation. If that is like if you have, again, simple example, an accelerometer, if your scale factor is 1% too large, then as you do a roll test, you'll go from 1G to 1G and 1% back to 1G. Whereas in this case, what actually happens for a non-orthogonality is it is at the intercardinal points that it's critical. So if your sensor is supposed to be aligned at, let's say, like a 90 tool face or a 180 tool face, the alignment error is too insignificant to really impact your total field. Again, you'd have to be off by a number of degrees. Where you see the deviations are when you're at like a 45-degree tool face, and so you get a slightly additional component from both sensors. Yeah.
If you have a scale factor, process sensor, let's say 1% around one, the other one is
Sure.
the same type of measurement. It's like this guy have a rough 50 to 5 figure. To take it down, you have a negative offset, but we have a figure in the other.
Right.
Yeah.
So for the scale factor, what you would actually see, if it were a scale factor error on this type of roll test, the peak would actually be at 90 for a tool face rather than 45. It would be when a single sensor is reading its full value as opposed to when both sensors are contributing. So that would be one difference. The other difference is that it would go from no delta, so essentially a correct reference, and it would either go high or low, but it would stay in that domain. So it would not cross from like a negative delta B total to a positive delta B total from a single sensor scale factor. And this is also, this isn't the way you solve for a non-orthogonality. This is just the way you talk to someone about it who's not doing the calculation. If you look at the actual inversions, they are not linear. Like they are separable terms that are distinct in terms of what they create. This is just a nice visual that when you're talking to a rig hand about why there's an issue with their tool, they at least agree that you should not see a double sine wave in a roll test like that. Any other questions? Well, thank you all. Oh, Robert.
It's not so much a question. I'm really not. I think one of the confusions is that we define the two axes as the axis of the tool itself. So each individual sensor, individual axis sensor, same with accelerometer, the alignment of that with its own bias and scale factor is then the alignment coefficients take it back to the tool frame of reference.
Yes.
Okay? And when we talk about bias and scale factor alignments, we then start talking about the way it's talked about here often is confusing the tool alignment with the individual sensor alignment. And those are what you're saying is that those sensor alignment coefficients from the manufacturer are not what you're talking about here to address.
Yeah, and there's, yeah, so and that's actually, there's actually one other nuanced point I glossed over. When we say scale factor, bias, and alignment for the purposes of this, we are talking about residual corrections. So you have a tool that was calibrated, it was giving you good readings, and its current performance is not exactly what that calibration was. And so it's the residuals after doing the calibration, which is also where, I think it was on the slide, I don't know if I talked through it, a good bit of this analysis has small angle approximations and some of the cross-sensor things assume that that sensor is very close to the true value for these assumptions to work. And so yes, so we're talking about residual alignment errors of the individual sensors to the tool chassis from their relative to their calibration. Yes. Exactly.
What you were looking at is
The performance of the tool. Yeah.
Model, the sensor model, and your tool performance model.
Right, because it's when you do, because it is the limits of the tool when you talk about QC processes and even arguably the performance specifications that are in the instrument performance model, you're not really talking about how that tool is going to work on its first job when it comes out of the shop. You care about what did it do on the last job before they sent it back. So what is the performance of that tool right before the field hand identifies that it's no longer in spec, and that's what you're really worried about quantifying. So that's where, yeah.
All right.